Testing, testing, testing. Testing, 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 testing. All right, and we're live. The volume works. Volume does work. All right, welcome to another Hoopo live stream. Today we're looking at a reinforcement learning paper coming out of Deepmind. This is relatively recent work coming out in January 2023. If watching this for the first time on the channel, we're using a program called Paperspace, which is a paper management tool. No affiliation, but definitely a good tool. So the name of this is Human-Timescale Adaptation in an Open-Ended Task Space, and the team has written this as, I guess, the Adaptive Agents team, and it's enough names that they have actually split it and put it in the back. So that's kind of interesting. I haven't seen that before. But yeah, it's probably like almost 20 people, so makes sense that they didn't want necessarily 20 people's names just polluting here and then causing all kinds of trouble in terms of figuring out whose name is first and whose name is second, and having like 10 different types of asterisks symbols to denote equal contribution. So I like this little innovation here of just putting it all behind the name of the team. All right, so foundation models. Okay, so foundation models basically refers to large models. It's kind of another way to describe them. So these are your clips, your GPTs, basically models that are several orders of magnitude larger than something you can train by yourself. They're trained by institutions, and they're trained on very, very large data sets that are, again, a couple orders of magnitude larger than what you could have and what you could get as an individual or as a small team. So pretty much the paradigm of deep learning in 2023 now is you start off with some kind of foundational model, and then you either fine tune it to your specific task, or you figure out how to use it in a zero-shot way. So I'd be curious to see if they're actually doing anything with a foundation model here. Maybe they use a foundation model for vision. Not sure. So far, these successes have not fully translated into reinforcement learning. I wonder if they consider Gato to be a foundation model in the reinforcement learning world. I don't think there's a formal definition for foundation model. I think it's literally just scale. If you have something that's big enough, you can call it a foundation model. So the Gato could be a foundation model. Gato is another reinforcement learning agent that they released while ago now, not even a while ago, last year. But they fed it with a huge amount of different tasks and different modalities of data. So it has kind of the general ability that you would characterize with foundation models. Right. In this work, we demonstrate that training an RL agent at scale, okay, so we're going to be doing a lot of training, leads to a general in-context learning algorithm. Okay, in-context learning. In-context learning is becoming more and more popular, but as kind of in the semantic and terminology world. But to me, I feel like it's, why not just use the word zero shot, right? Adapt to open-ended novel that can adapt to open-ended novel embodied 3D problems as quickly as humans. So this is the actual task space. In a vast space of held-out environment dynamics, our adaptive agent, ADA, displays on-the-fly hypothesis-driven exploration, efficient exploitation of acquired knowledge, and can successfully be prompted with first-person demonstrations. Okay, so we're going to be seeing some behavior cloning, what first-person demonstrations are. We are going to be seeing some curiosity type metrics, exploration rewards. Exploitation of acquired knowledge, perhaps some kind of value function. Adaptation emerges from 3 ingredients: meta reinforcement learning. Okay, so reinforcement learning, and then the word meta there means at a higher level. So learning to learn is another way to describe meta learning. Policy parameterized by a large-scale attention-based memory architecture. Okay, so they're gonna probably be using a big transformer in here, especially since they mentioned training an RL agent at scale and then a large-scale attention-based memory architecture. Basically, they're going to find the biggest transformer that they can reasonably fit and train it for the largest amount of time they can reasonably argue to their superiors, right? Because there's some limited amount of budget for this, and if they could spend $1 billion, you could spend $1 billion training. Effective automated curriculum. Okay, this is interesting. So curriculum, right? People are familiar, kind of in a university or in a school setting. Curriculum is the series of lessons, right, that has been chosen to teach a certain subject. And the same way that you could choose kind of a curriculum for a class or a course in a university, you can also have a curriculum for a reinforcement learning task, where you basically have easier tasks that eventually lead to harder tasks that eventually lead to harder tasks. So curriculum learning is actually more and more popular in reinforcement learning, I feel, and it's kind of shows that as a field we're moving from these simple tasks and moving into more complicated tasks that require kind of a curriculum leading up to them. We demonstrate characteristic scaling laws with respect to network size, memory length, and richness of the training task distribution. Okay, so big models and big data are still king. And finally, we believe that our results lay at the foundation for increasingly general and adaptive RL agents that perform well across even larger open-ended domains. My face is unnecessarily big. Let's make it a little smaller. Yeah, how about that? All right, perfect. So here we have kind of a top-down view of this environment before. If you guys haven't seen it, I think this is the agent. It looks like a little capsule, as it's called. This is like a game engine. It's probably Unity, if I had to guess. And basically this little agent, it's embodied. So saw the use of the word embodied here, and what that means is that the agent can basically control its position in this environment, right? So it has access to probably rotation, the rotation of its body, and then the forward motion of its body, perhaps backwards motion and lateral motion as well. That's what the action space is. And usually they do these with a camera as well. So the agent has basically a little forward-facing camera on the capsule, and then it can move around in this world and interact with this world. So think of it like a little video game character, but the official terminology for this kind of agent in this kind of environment is called embodied, right? It's the fancy word that reinforcement learning people use. All right, so here we go. Figure 1, human timescale. Example trajectories. A trajectory is basically the position and path the robot takes over the course of a specific time-gated task, right? So like the task, there's some total time that you spent performing this one task, and that total amount of time you're going to have at the individual kind of micro level, you have a bunch of actions. So turn left, move forward, move forward, move forward, turn left, move forward. Those are like little individual actions. And the collection of all these actions from the beginning to the end of what is called a trial, right? Or an episode sometimes in reinforcement learning, that's going to be called the trajectory. So these are trajectories. It started here, and then you can see it kind of moved and then swooped around and picked up, I guess, this object and then dropped it here and then kept moving and then grabbed this object and then put it there. Initial trials show a policy that uncovers hidden environment dynamics after just seconds of test time. ADA finds a valid solution to the task. Okay, so they're showing you here score 0, so the agent was unable to achieve any reward. There's probably some kind of puzzle here to solve, right? Where you have to kind of move specific objects in contact with other objects. So that's why kind of exploration is important, because the agent is not told what the task is. It has to kind of discover the task through trial and error. And here you see score 13, score 16. So it's showing you how the agent can, over the course of multiple trials, eventually learn what the task is. The dash colored lines show the agent carrying an object of corresponding color. For a full description of tasks, see figure B1. All right. Available on our microsite. What is a microsite? It's a tiny site. That. All these YouTube videos. Pretty cool. All right. Let's continue. The ability to adapt in minutes is a defining characteristic of human intelligence. I don't know about human intelligence. I feel like a lot of animals have this ability. Crows, dolphins, elephants, and an important milestone on the path towards general intelligence. Given any level of bounded rationality, there will be a space of tasks in which it is possible for agents to succeed by just generalizing their policy zero shot. Zero shot. But where progress is possible if the agent is capable of very fast in-context learning. So to me, zero shot and in-context learning are kind of the same thing, right? Zero shot just refers to that you're taking a neural net or a model, right? Or in the case of reinforcement learning, a policy. That's what they call the neural net inside an agent, right? They call it the policy, but it's really just a neural net. When you apply it to a new type of problem without doing any additional fine tuning, you call that zero shot. The context is basically when you are performing a certain task, such as here in this little thing, there's some kind of memory that's being stored intermediate, right? So that's called the context. So for example, in GPT-3, the words that you type at the very beginning of the conversation, and then kind of as you keep talking to GPT or ChatGPT, there's a context that you're building there, right? And in-context learning refers to the fact that as you accumulate this context, your the model, right, the neural net is actually changing the way that it responds to the inputs and outputs, right? So you're not actually pushing gradients. So it's not learning in the sense that you're pushing gradients into the actual network. It's learning in the sense that the context that it has accumulated is becoming useful in improving the performance on the remainder of the task. So to me, they're both the same in that in both zero shot and in context learning, you're not actually pushing any gradients into the actual model. So maybe in context learning is contained within zero shot. I think would be the most accurate way to semantically define those two terms. But they're more the important thing is that they're more similar than it would appear. At the end of the day, zero shot and learning, neither of them is pushing gradients into the neural net, into the model, into the policy. The policy is unchanged. Basically, what they're going to show is that the policy that they've trained can efficiently make use of the memory or the context that it gathers over the course of some kind of episode. So either the context is kind of shared between these different trials somehow, like it when the agent is here, it has the context of this previous trial, or the context simply refers to basically when the robot is here, the context refers to the path that it took to get to there. Useful in the real world and in interaction with humans, our artificial agents should be capable of fast and flexible adaptation given only a few interactions and should continue to adapt as data becomes more available. Operationalizing this notion of adaptation, we seek to train an agent that, given a few episodes in an unseen environment at test time, can accomplish a task that requires trial and error exploration and can subsequently define its solution. So, okay, I think this is going to be the context. And maybe this is why, because this is something a little bit different. Normally, in reinforcement learning, each trial is individual, right? So in between trial 1 and trial 2, the memory is wiped. But the way that they're phrasing this, given a few episodes, it seems like the memory is not wiped. So the context for trial 3 is not just the memory of whatever you're currently doing in trial 3, it's also the memory of what you did in trial 2 and what you did in trial 1. So playing with the context length there, I think, is an interesting thing, and not just resetting the context every time. So that could definitely be something interesting that they do here. Meta-RL has been shown to be effective for fast in-context adaptation. However, Meta-RL has limited success in settings where the reward space is sparse and the task is vast and diverse. So what does it mean that the reward space is sparse? So reward is this here, right? Score 0, score 13, score 16. And the way that reinforcement learning works is it's trying to maximize the expected return of that score. So it's trying to get the highest score, right? And whenever a human designs an environment, and these environments are designed by humans, there is a certain score that is given. And the sparsity of that score refers to how well that score is kind of distributed throughout the trial. So let's say that, for example, for completing this task, you only get reward at the very, very end. That would be a very sparse reward because there isn't any reward until the very end. But let's say that you get a reward for moving into this gray area, and then you get a reward for touching this black triangle, and then you get a reward for dropping the black triangle. So that would be a dense reward, right? Where you have a lot of intermediate rewards for the reinforcement learning agent to learn from. So they're basically saying here that Meta-RL doesn't work great if the reward is sparse and the task space is vast and diverse. So the task is the actual environment. So the task is vast and diverse is basically another way of saying it changes a lot, right? So I assume that this little map here that they have is not actually static, that they basically randomize this. They use kind of domain randomization to create basically a new environment every time. Right, they have random seed that determines the position and location of all the different things, probably even the color of the different things as well. So you have a vast and diverse task space, and you have a potentially sparse reward, which means that Meta-RL is going to have a problem on that. Outside RL, foundation models and semi-supervised learning have generated significant interest. So foundation models again here, and then semi-supervised learning is perhaps, so supervised learning is whenever you have a labeled data set, right? You have inputs and outputs, and of course the output has been painfully annotated by some humans or collected in such a way. Semi-supervised learning means that you're either doing some kind of auto-labeling, or the labels from which you're doing the supervised learning are in some way generated. Due to the ability to adapt in a few shots from demonstrations across a broad range of tasks. These models are designed to provide a strong foundation of general knowledge and skills that can be built upon and adapted to new situations via fine-tuning or prompting with demonstrations. Okay. I see what they're going to be doing here. So the use of the word prompting with demonstrations, this is important to me, right? You see kind of what they're setting up here. They're saying in-context learning, prompting from demonstrations, in-context adaptation. So I bet you that what they're going to do is that the context is basically maintained throughout each trial. So I bet you what they're going to do is the first one is going to be a human. So a human will drive the little agent and will complete the task, right? And that will you can think of that as the prompt, right? Where the human has created the first part of the context, which we're going to call the prompt. And then the agent is given control in subsequent trials, and then it learns, not in the sense of actually pushing gradients, but learns in the sense that it can observe the previous part of its context, or the prompt in this case, and perform better from that. So that is different than the way that demonstrations have classically been used in reinforcement learning. Normally in reinforcement learning, when you're doing behavior cloning or demonstrations, you're collecting a bunch of human trials, right? And then you're pushing gradients from those, right? So then you're basically using supervised learning to say, hey, this is what the human did in this particular place, and I'm going to push a gradient into the actual policy, into the actual neural net within the little reinforcement learning agent's brain, such that it mimics the human, right? And that's what behavior cloning is called. But it seems like here, the way that the human demonstrations are going to be used is they're going to be used as basically the beginning part of the context. So that is very cool. That is different from kind of the generation of RL that I did, and you can see how foundation models and this idea of in-context learning is kind of spreading from language models and into the reinforcement learning world. So it's good to see them using stuff like that. And then, of course, everyone uses transformers, so which show power law scaling in performance with the number of parameters. Yeah, this is another term that has kind of been popping up more and more, power law scaling. So they're just kind of giving official terminology to the fact that bigger models and bigger data perform better. But I feel like people have been kind of obsessed with this word power law scaling. Who love to come up with terminology. All right, so what do we got here? Figure 2, training or adaptive agent. So ADA means adaptive agent. They're probably going to start using the acronym as soon as they start doing this. Train a large transformer model with meta RL in Excel and XLand. Okay, so this is probably the environment. So it's like the environment generator. It's probably based on a game engine. I had to guess Unity. During training, tasks are uniformly sampled and subsequently filtered to produce an ever-changing training pool of tasks at the frontier of the agent's capabilities. After training on these tasks, the agent is capable of adapting to unseen hand-authored tasks as effectively and efficiently as humans. Cool. So you have XL task pool, or XLand tasks pool. So I guess here they're kind of showing you that there's kind of some infinite universe of possible environments in which they're calling tasks, right? Which is some map with some specific goal and some specific reward. And of course, there's an infinite amount of them because there's probably every single variable inside this environment is randomized, right? Like the number of levels, the number of sizes, potentially even the size of the map, the colors, all of it. So uniform sample, I guess here they're sampling every single possible, or sampling some subset of all possible tasks. Select the tasks above the fitness threshold. Okay, so I guess they just naively apply the reinforcement learning agent to their sample of possible tasks. Some of them are going to fail, some of them are going to succeed. What they're going to do is it seems like they're going to take the ones where they succeed and add them to the training set. And then that's going to be the data upon which the policy, or the neural net here, ADA, trains. Train the agent, RL update, distillation. So this is the actual pushing the gradient, and then distillation might refer to the fact that there's different models here. You have a big model that trains a smaller model, potentially. And here's what the actual agent architecture looks like. You have observations, which are probably going to be images coming from this environment. And then you have the value. So in reinforcement learning, you're basically one of the things you're learning is called a value function, right? You're trying to approximate, you're using a neural net, which is a very good function approximator, to approximate what's called the value function. And what the value function tells you is the reward. It's the score. So the value function is basically the best guess as to what the score is going to be at this moment in time, right? So it's important that a reinforcement learning agent has the ability to think about what the score is, what the value of a certain action at a certain space or a certain point in time and space is. And then of course the action is that kind of like microscopic movement that it does, right? So move left, move right, so on. And the way that they're putting it here, like you see how there's a width here, there's 3 dots. It seems like it does it all, right? So it does from point t, or from time t, all the way to time capital T. So it probably doesn't just predict the immediate value and the immediate action, but it also predicts the value and the action for every subsequent step in the episode. In this work, we pave way for training an RL foundation model. Okay, so this is really what Deepmind wants to do, right? They want to train a foundation model for reinforcement learning that they can then zero-shot apply to a bunch of real-world tasks. And I thought that's what Gato was, to be honest. So I don't know. It seems weird that they're denying the existence of their previous work, which to me is a type of foundation model. Okay, this is actually what I said, but in a better sentence. So let's read it. An agent that has been pre-trained on a vast task distribution and that at test time can adapt few shot to a broad range of downstream tasks. Why few shot? Just zero shot. We introduced adaptive agent, an agent capable of human timescale adaptation. I wonder what human timescale here means. Does it just mean seconds? Does it mean hours? Does it mean 100 years? ADA does not require any prompts, fine-tuning, or access to offline data sets. Depends on what your definition of prompt is, right? You're using a human expert to create a context. Is that prompting? Data acquires knowledge efficiently, adapting in minutes on challenging, held out, sparse reward tasks in a partially observable 3D environment. So partially observable 3D environment here. So sometimes in these reinforcement learning environments, the agent kind of cheats. So you see this all the time, but like the agent knows exactly where everything is. So for example, in the OpenAI Dota paper, the agent, the reinforcement learning agent that's playing one of the characters in the Dota video game, it knows the exact position of everything in the screen, right? So it's not that it's looking at the pixels on the screen and making decisions based on that, right? It has full observability. It knows exactly where, how far away it is from the enemy players in that. So I think partial observability is key. And I think that moving forward in reinforcement learning, you want to make sure that the agent, the policy, only has observability over a subset of the things in its environment, right? The set of all observations and the set of observations the agent has access to, there should be a difference there, because as a human, that's the way it is too, right? I don't actually know what's behind my head, and that's important. Human study confirms that the timescale of Ada's adaptation is comparable to that of trained human players. I wonder who they're paying to do that. Ada's adaptation behavior in a representative held-out task can be seen in Figure 1. Ada can also achieve improved performance through zero-shot prompting with first-person demonstrations, analogously to foundation models in the language domain. Zero-shot prompting with first-person demonstrations. Okay. We're just bouncing around different terminology to describe the same thing. We use transformers as an architectural choice via model-based RL squared. So Model-based here, model-based has a specific definition within reinforcement learning, and what it refers to is that there's types of reinforcement learning that try to create what is known as a world model. So a world model is basically a neural net or a model, right? It doesn't need to be a neural net, but it pretty much is a neural net every single time. It's a neural net that can predict the world, right? Given a current state of the world, it predicts the next state of the world. So given an action, it can predict how the world changes in response to that action. So you're building a model of the world, right? So understanding of the world is another way to describe model-based RL, where it's almost like a religion, to be honest. Like there's people who are model-based, people who are not. And in model-based RL, one of the key assumptions is that you need to be able to predict the world in order to effectively perform tasks in that world. Foundation models typically require large, diverse data sets. To make this possible, where agents collect their own data, we extend the recent XLand environment, producing a vast open-ended world with 10 to the 40 possible tasks. Yeah. Oh, I mean, so one thing to always remember here is that even though it says 10 to the 40 possible tasks, and this is such a vast, diverse world, the reality is that it's constrained, right? So, like it's not really 10 to the 40th. It's still a very constrained environment in that all the pieces that you're using to build it are the same. It's just the permutation and combination and placement of those things that is different. These tasks require a range of different online adaptation, including experimentation, navigation, coordination, division of labor, and coping with irreversibility. Okay, so they're probably going to have kind of tricky things, right? So the way that these tasks are defined, there's probably going to be certain things where if you accidentally move this object, then it's over and there's nothing you can do. So things like that, irreversibility. Make use of adaptive autocurricula, so some kind of automatic curriculum generation. Finally, we make use of distillation, which enables scaling to models with over 500 million parameters. So largest model ever trained from scratch. There you go. This is what I want to see from a Deepmind paper. Tell me that you guys are pushing the envelope when it comes to training time and training size and model size. That's what I want to see, like a company like Deepmind that has kind of infinite money from, of course, Google and Alphabet, which are the parent companies that own Deepmind. I want to see massive training budgets. I want to see huge models, right? I really want to see what the state of the art, what we can really do if we push our compute and model size to the very limit. So glad to see that they're doing that. And then, of course, at the end of the introduction, you're going to have a bulleted point list or a numbered list of actually everything that this paper is going to promise and everything that this paper is going to do. So here we go. Here it is. We introduce ADA, agent capable of Human-Timescale Adaptation. Okay, so an agent, neural net, a policy. Train ADA using meta-RL at scale, so open-ended task space with an automated curriculum. Okay, so they're basically going to be training it on a bunch of variants of some kind of task. They're calling it an open-ended task space, but at the end it is kind of constrained. It is constrained. It's just procedurally randomized within the constraints. And then they're going to be crafting curriculum. So like there's going to be some kind of like clever way in which they create harder or easier versions of the task that lead to harder versions of the task. Show that adaptation is influenced by memory architecture, curriculum, and the size of complexity of the training task distribution. Okay, so they're going to show you that the power law scaling is in full force here, that as you probably increase the size of the model, as you increase or make the curriculum better, which is kind of making the training data set better, and increase the size of the training data set, you're going to get a better agent, which I think most people would have guessed. And we produce scaling laws in both model size and memory and demonstrate that ADA improves its performance with zero-shot first-person prompting. Okay, so if you're doing in-context learning, if the context that you're learning on is created by a human expert person, of course it's going to be better. To achieve human timescale adaptation across a vast and diverse task space, we propose a general and scalable approach for memory-based meta-RL, producing an adaptive agent. We train and test Ada in XLand 2.0, an environment supporting procedural generation of diverse XLand 2.0, I guess, and multiplayer games. Curriculum to guide the agent's learning, a model-based RL algorithm to train agents with large-scale attention-based memory, and distillation to enable scaling. So what does distillation to enable scaling here mean? So the big model would be too big to actually use effectively, right? Especially in a reinforcement learning context where in order to get data in reinforcement learning, you have to actually perform trajectories, perform rollouts, perform episodes. And part of that trajectory, part of that episode, you're going to have to perform a bunch of inference, right? Every step that the agent takes is one inference that you have to perform. So if you have to perform inference on a 500 million parameter model, it's going to take you very, very long to collect a huge amount of data. So I bet you what they're going to be doing is they're going to have the much bigger model. They're going to train that, and then they're going to use the bigger model to distill to a smaller model, right? And then that smaller model is probably going to be the one that they actually use whenever they collect experience. And the actual benefit of that too is that there's actually more randomness then, right? Sometimes you have issues where in reinforcement learning where if your reward is not nicely shaped and your agent finds some kind of trick, it'll kind of like just like focus on that trick and just greedily exploit that part of the environment, that part of task space. So a lot of times you have to add randomness, either explicitly by saying, okay, this is the action that the agent wants to take. Let me add some randomness to it so that it takes a slightly different action. But one way to kind of add a little bit more noise, a little bit more exploration is probably through distillation, right? So take that big model, use it to distill a smaller model, and that because you're going through that distillation process, that smaller model isn't necessarily going to take the action that the big model would take every time. So if you have a variety of different distilled smaller models, you're going to have a little bit more randomness there too, because each of those little small models might do weird things, which will allow you to more efficiently explore the task space. Okay, here they describe the open-ended task space. We extend the procedurally generated 3D environment. Game, a world, and a list of co-player policies. Goal per player defined as a Boolean function on the environment state. Okay, so this isn't great because this means that this to me suggests that there's a very sparse reward signal, whereas basically you get some reward for completing the task and then no reward for doing anything intermediate. So generally in reinforcement learning, the more sparse your reward signal is, the harder it is to actually learn anything. World specifies a static floor topology. It's not good. Via first-person pixel observation, that's good. So I actually had a very similar project to this myself. So this is some throwback, but this project here, Pirate AI, I made this a very long time ago, 6 years ago. And you can see here, I had a very similar type of situation where you had these little pirate capsules that were moving around in this environment and trying to find the treasure. And I used more of kind of an evolution-based algorithm where I would pit them against each other, and then the ones that succeeded would keep going and so on. But what I'm showing you this is that, right, the little pirate has, it's looking, it has basically a first person view of the environment. That's what it's actually using to determine what's going on. So you can see here, this is what it can see. Here's the camera preview. That's what it's seeing, this little agent. So basically this agent here is doing the same thing, first person pixel observation. Okay, so they're adding something here they call production rules, condition, blah, 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 possible. So, okay, here they're just kind of describing their environment, which is not important, right? At the end of the day, we're interested in reinforcement learning, not necessarily the mini game that they've crafted to create or that they've crafted. So there's some kind of mini game that involves like these objects, and you have to like grab objects and touch specific objects to other objects, right? And I'm sure they sat there and thought about making this as cool as possible, but it's not super important to know what that is, right? Because that's just like the game logic of the game that the reinforcement learning is learning to play, but we're more interested in actually the reinforcement learning itself. Okay, trials and episodes. One episode equals K trials. Okay. So this is interesting because normally in kind of other reinforcement learning work, one trial would be the episode, right? You start the trial, you try to do the thing, and then when it ends, that's it. But you see here, they're being very clever and they're resetting the environment, but keeping the context. So the agent memory does not reset. So the agent gets multiple attempts at the same task, which means that it can learn from its previous attempts. And this is very clever. And I think this is kind of where they're getting inspired by this idea of in-context learning, especially if you start putting human demonstrations as the first trial and then give the agent the next 2 trials to do it themselves rather than letting the agent just zero shot go 3 trials in a row. Trial duration varies across tasks, so it's not going to be necessarily 3 trials. You can have a task that's shorter, and I guess you have 5 trials. Here's a different task. Pass over wall repeatedly. And you can see here the XLand 2.0 environment. There's potentially hundreds of these different types of tasks that require slightly different things. Tool use, irreversibility, information asymmetry, division of labor, experimentation, navigation, like so. I mean, at the end of the day, it seems like they're all kind of variations of like touch specific objects and move on in a specific place, and you have to touch this before this. But there is a kind of an infinite amount of these, or not infinite, but 10 to the 40th, which is might as well be infinity. Hiding an object, hiding a condition's predicate. Okay. We pre-sample a large pool of tasks instead of procedurally generating tasks on the fly. So the reason they probably do this is because these tasks are implemented in a game engine, and it's probably computationally much more efficient to pick the task and then create kind of a game executable from that specific task, and then use that game executable to collect experience. It'd be a lot more annoying if you had to basically define the task and then build the game and then run that game. So I think this is coming kind of from the fact that they're using a game engine, and the game engine has a specific kind of workflow where you have to define the environment, define the assets that are used in that environment, define the different textures, and then build that, right? Kind of similar to the concept of compiling code. You have to build that into an executable, and then that executable can run. So that's probably where that's coming from. Meta RL. We use a black box meta RL setting. We define this task space M to be a set of partially observable Markov decision process, POMDPs. So Markov decision process, it's complicated. I don't like the Markov decision process, but pretty much all of reinforcement learning is based on this idea. And the Markov decision process is this idea that you can take an environment and break it down into basically a graph where you have things called a state, you have things called actions, that taking the same action in the same state will produce the same subsequent state, right? So is this idea that the world is kind of like fully deterministic, that any state, any action, and any pair of those produces the same thing over and over again. And this comes from the history of reinforcement learning. And like one of the things that they used to do way back in the day is they would create these tables, right? Like a big table. And in that table, they said, okay, I took this state at this action, and this is what I got, and I'm going to write that little value in. And it's important that the whole world is discretized because I need to be able to fill this entire little table with numbers. And eventually they got rid of those tables and they replaced them with neural nets, but they kept this baggage around, this kind of like Markov decision process. And I think that the reason I don't like it is because I don't think that the world is as deterministic as the Markov decision process makes it be, right? I think that there's kind of, I don't know what it is, but I feel like there's something more more accurate, more simple than a Markov decision process that would potentially even unlock reinforcement learning into a new kind of like level, right? But there's so much formalism, so much like mathematical baggage that people have built over time in the field of reinforcement learning that it's basically impossible to find a reinforcement learning paper that doesn't start with Markov decision process as the base layer of reality, right? And here the partial observability just means that the agent in this state or the agent in this Markov decision process world only has access to a subset of the state, right? It doesn't know the actual state, it knows its observation on the state. And partially observable Markov decision process is in a sense an attempt to basically make the Markov decision process a little bit more realistic. They're saying, okay, well, obviously it doesn't make any sense that you would know the entire state in the Markov decision process, so let's add this partially observable part to the front of it, and then we can pretend that now it's a good thing to do. But I still feel like, to me, the Markov decision process is still no good. I don't know what to replace it with, but I just don't like it. Okay, so you have some specific task M. So task space M is all possible tasks, and then task lowercase m is going to be sampled from that all possible task space. You find a trial to be any sequence of transitions from an initial state to a terminal state. Okay, so you have S0, then you have S of capital T, where T is going to be the time. Tasks terminate if and only if a certain time period has elapsed. Okay, so this is where the human timescale comes, where they're deciding that 10 seconds is kind of a human timescale, and then every single state or every single task is going to be limited to this particular time period. The environment ticks at 30 frames per second, very standard video game frame rate there. And the agent observes every 4th frame. So this is interesting. I hope this is not what they mean by partial observability, but only every 4th frame do they use. And this is something that I did as well for my project, my ancient project at this point. But basically the problem is that at 30 frames per second, you get a lot of duplicate frames. You kind of get the same frame over and over again because 30 frames per second is quite fast. So you want to get rid of some of that data. So reducing it basically every 4th frame means by 25%, or you're ultimately using 25% of the data, which I think is better. And of course, if you do 10 seconds times 30 frames per second, and every 4th frame, you end up with a range of 75 to 30. So there's basically each trial or each task is going to roughly contain 75 steps or 300 individual steps. Episode consists of a sequence of K trials for a given task M. Okay, so K trials. At trial boundaries, the task is reset to an initial state. In our domain, the initial states are deterministic except for the rotation of the agent, which is sampled uniformly at random. Okay, so the agent starts in a specific place. So the task determines where the agent starts, but then it can be randomly rotated. Black box meta RL training, an agent uses experience of interacting with a wide distribution of tasks to update the parameters of its neural network. So this is the meta part of the meta RL. So it's meta in that it's not learning to perform a very specific task. You're pushing gradients from a huge variety of tasks, right? So the agent is not getting better at that specific task. Every gradient update doesn't make it better at that specific task. It makes it better at all specific tasks. So, for example, meta learning outside of reinforcement learning, one of the ways that you could do that is you could have a classification problem and a regression problem, and both of those have slightly different loss functions, and then you alternate between that. So you push some gradients from the regression task, some gradients from the classification task, and then eventually the model that you have is going to be hopefully good at both of those, or at least better at more general than an individually trained agent trained on an individual thing would be. If an agent, okay, so the neural network here parameterize the agent's policy distribution over action. So there's a lot of stuff here. So I apologize. The reinforcement learning is pretty dense, so it can be difficult to parse these papers. But basically, the neural nets inside the agent's brain, right? What's normally called the policy. Policy is kind of another word to describe that. They usually don't output a raw action, right? So the way that, for example, I did it, they did output a raw action. So my agent would take an image, it would feed it through a convolutional network, then through some fully connected layers, and then it would output one of 4 actions, right? Move forward, move left, move right, or turn left, turn right, move forward, move back. But when you're doing reinforcement learning with the big boys at Deepmind, you're not outputting actions directly. What you're outputting is the parameters of a distribution, right? So I think yesterday, or maybe not yesterday, but we were looking at the Gaussian distribution, right? And Gaussian distribution is just the bell curve, the normal bell curve, right? But a Gaussian, right, is parameterized by these 2 numbers here. So it's parameterized by the mean, mu, and the sigma here, which is the variance. So the shape and the size of this distribution, this normal distribution, this Gaussian distribution, is parameterized by these 2 numbers. If you give me these 2 numbers, I can give you this distribution. So in reinforcement learning, what the neural network outputs is not the actual action. What it is these 2 numbers here. It's basically the 2 numbers which define a distribution, and then the actual final action that it takes is a sample from that distribution. So it's not necessarily a Gaussian or a normal distribution, but it's outputting the numbers that parameterize a distribution, and then the action that it takes is a sample over that distribution. If an agent possesses dynamic internal state, then meta-RL training endows that memory with an implicit online learning algorithm by leveraging the structure of repeated trials. Okay. At test time, this online learning algorithm enables the agent to adapt its policy without any further updates to the neural network weights. Again, this is the same thing that they're referring to with the in-context learning, except here they're calling it implicit online learning. So I feel like RL people are a little bit pompous and needlessly verbose. Right? They're not trying to make these things easier for other people to read, and it doesn't seem like they're being inviting towards people to come and into that community and help and contribute. They hide behind this kind of historical volume of work and terminology. Markov decision processes, the zero shot, meta-RL, implicit online learning, in-context learning. Like, don't let the jargon scare you. The concepts underlying these things are actually more simple than they seem. It's just that the jargon and the terminology are almost purposefully designed to obfuscate. Swag it is. At test time, this online learning algorithm enables the agent to adapt its policy without any further updates to the neural network weights. Yeah, so again, in-context learning, online learning, whatever they're doing here, implicit online learning, you're not actually pushing gradients into the neural network, right? The neural network is just changing its behavior based on the context. Therefore, the memory of the agent is not reset at trial boundaries, but it's reset at episode boundaries. To generate an episode, we sample a pair, m, k, where k goes from 1, 2 to 6. Okay, so k is the number of trials. So here you see how the yellow task here, there's 5 trials per episode, and then here in this blue or cyan or whatever this is, there's or turquoise, I think, right? There's 3 trials. So k can go from basically 3 to 6. Or I guess k can go from 1 to 6. At test time, it is evaluated on unseen, held out tasks. And I feel like this is a little bit strong because it's not unseen, right? At the end of the day, the task space itself, despite what they're saying here, that it's so broad and it's so wide and it's so whatever, like they're all kind of the same, you know. At the end of the day, like all of these tasks, it's all variants of the same kind of thing, the same objects, same kind of idea, same kind of environment, same kind of like movement and all of that. So it's not like they're taking something that was trained on a robot arm and then trying to put it on a robot dog. You know, it's like that's what I would say is like an actual real unseen held out task, actual zero shot. Right? Here they're just saying unseen and held out in the sense that the agent hasn't seen that specific permutation of the task, that specific version of the task. But to me, this task space is so similar that is it really zero shot? Is it really adapting? Is it really seeing something it hasn't seen before? Or is it just kind of the same thing that it's been seeing? Auto-curriculum learning. Given the vastness and diversity of our pre-sampled task pool, it is challenging for an agent to learn effectively with uniform sampling. Most randomly sampled tasks are likely going to be too hard or too easy to benefit an agent's learning process. Instead, we use automatic approaches to select interesting tasks at the frontier of the agent's capabilities. Analogous to the zone of proximal development in human cognitive development. Yeah, so this is a paper that sometimes people mention in reinforcement learning. Again, we within machine learning, we love to kind of show how some of the things that we do are actually coming from a biological model or biological kind of inspiration. So obviously neural nets are inspired by the way that the neuron cells in your brain are connected to each other and the way that they fire and so on. And within human cognitive development, I don't know exactly, I haven't read this paper, but I think this is the paper where they say that you want to be failing 50% of the time, right? So when you're trying to teach someone how to do something, you don't want it to be the case that they fail every time, and you don't want it to be the case that they never fail, right? You want them to fail exactly something like 50% of the time. So as the person gets better, you make the thing harder. And they're kind of drawing an analogy here that it's similar to that, right? Where choosing a curriculum, making sure that the agent is having a hard time in the specific task and it's not too easy, it's not too hard, is similar to the way that you actually teach humans to do things. Emergent curriculum. I don't know if I would call that emergent, but it's a curriculum which is chosen automatically. We extend the dynamic task generation method to our setup. When a new task is sampled from the pool, it is first evaluated to assess whether ADA can learn from it. We evaluate ADA's policy in a no-op control policy. Okay. So no-op, no operation, basically means the little agent is just sitting there and it does nothing for a number of episodes. Task is used for training if and only if the scores of the two policies meet a number of conditions. We extended the list of conditions from original no-op filtering and then used normalized thresholds to account for different trial durations. Prioritize level replay. We modify robust PLR. Okay, so PLR, prioritize level replay, seems to be a paper here. Here's good old Schmidt-Huber, so I'm sure he's glad that they're citing his papers. PLR uses a fitness score that approximates the agent's regret for a given task. Don't know what regret is, but it's probably, I don't know. Hopefully they define it. The reinforcement learning is filled with these kind of ideas like a fitness score and agent regret, right? And like curiosity, things like that, where people will come up with a human word which has some specific meaning and connotations within the context of human learning, and then they'll create a mathematical concept, an equation, some kind of process in the world of reinforcement learning, which is analogous to the human concept. But problem with that is that the human concept is kind of broader and allows for a lot more interpretation. And that sometimes, right, by formalizing something like fitness or something like regret or something like curiosity into the very constrained mathematical box of a Markov decision process and reinforcement learning, I think it can constrain needlessly kind of the idea, right? So some guy comes up with, this is what curiosity means in the context of a Markov decision process. And then from that moment on, everybody that works in that field is kind of constrained to use the word curiosity in that specific terminology, in the way that it was defined in that paper, right? So sometimes this can cause issues. And actually, I think that's what this is here, right? Note that we used a reverse naming convention. In our convention, trial maps well to other related concepts. Yeah, so this is the problem, is that some guy, this guy here in 2017, decided this is what a trial is and this is what an episode is. And then that kind of makes it hard to come up with a different or a new or kind of something outside the box, because you need to use the same terminology as everybody else, right? There's this kind of like formalism that comes with math where you have to make sure to use the same terminology as everybody else to make sure you're speaking the same language. But when the terms in that language are like somewhat arbitrarily picked and then it's hard, the mapping isn't perfect, you can result in these type of situations here where the terminology changes over time and these papers become very confusing as a result of that. Okay, so where were we? We were here. We consider several potential estimates for agent regret ranging from TD errors. Okay, so here you go. The agent regret, they have several different versions, several different definitions for that. TD errors, TD is temporal difference, and this is basically what reinforcement, this is one of the key parts of reinforcement learning, where they're basically, this is how value functions kind of creative. Let's see if there's a better definition of TDR. Temporal difference learning. Temporal difference learning refers to a class of model-free. So model-free there means you're not actually modeling the world, right? You're not creating a model of the world. You're simply performing or pushing gradients into your policy, and then that policy is going to be the best. So bootstrapping from the current estimate of the value function. So the value function is, again, your neural net that tells you what the value at this particular state is with this particular action. PD methods adjust predictions, blah, blah, blah. This is the reward. This is the discounted reward. Expected value of an action sampled from a policy. The summation over all time steps. So this is kind of the state value function of the Markov decision process, d pi. PLR operates by maintaining a fixed size archive containing tasks with the highest fitness. We only train ADA on tasks sampled from the archive, which occurs with probability p. Okay, so they have the XLAN 2.0, which has every possible type of task within this task space. And then they have a separate, what they're calling here, a archive, which contains tasks that have the highest fitness score here, right? So this is kind of the way that they're going to be choosing their curriculum, is basically sampling from this fixed set of archive and probably taking things out of that archive and putting things into that archive. Yeah, so with probability 1 minus p, a new task is randomly sampled and evaluated, and the fitness is compared to the lowest value in the archive. So they basically, if the new task has a higher fitness, it is added to the archive, and if the lower fitness task is dropped. Thus, PLR can also be seen as a form of filtering using the dynamic criteria. It differs to no-op filtering in that the task can be repeatedly sampled from the archive as long as they maintain high fitness. To apply PLR in our heterogeneous task space, is it really heterogeneous or is it just homogeneous? We normalize fitness at each trial index by using rolling means and variances, and use the mean per time step fitness value rather than the sum to account for varying trial duration. Okay, so because the different trials, tasks are going to have different amounts of trials, and each of those trials are going to have different amounts, different durations. You have to be careful about the score here that they're using to rank these tasks according to their fitness. So you have to adjust for that. Finally, since we are interested in the tasks at the frontier of an agent's capability, we use only the fitness from the last trial. Okay. Yeah. We are already at an hour and we're only 6 pages in. Holy shit. We're now ready to get done. All right, RL agent. We use Mwesley as our RL algorithm. All right. What a weird name. We briefly describe the algorithm here, but refer the reader to the original publication for details. Taking a history-dependent encoding as an input, in our case, the output of an RNN or transform. I somehow gave myself hiccups. Let me see if by drinking again I can remove them. Okay. So RNN, recurrent neural network, transformer, attention-based neural network, and then LSTM is a long short-term memory. Reinforcement learning used to be all about RNNs and LSTMs, but of course the overwhelming success of transformers in natural language means that computer vision started using transformers, and then they found out that vision transformers are actually very good. And now, if transformers are taking the NLP community by storm and they took over the vision community by storm, you can bet your ass that the reinforcement learning community is going to start using transformers. So it makes sense that they're going to use transformers now instead of RNNs. Okay, so predict the values v hat I, action distributions pi hat I, and rewards r hat I. So the values are, again, your estimate of the reward at a current state. So this is basically how good are you doing at this task at this particular moment in time. Action distribution. So again, the policy, the neural net that's inside the little agent's brain, it outputs the parameters of a distribution, and then that distribution is sampled to create action. So the action distribution, you can think of it like the actual what the agent is actually doing, right? So like move forward, turn left, like things like that. Pick up object, that's going to be what the action distribution defines. And then the rewards, that's coming from the environment, right? So the environment is omniscient and it knows everything. And as soon as the agent touches object 1 to object 2 or moves in a specific place, the environment can give it reward, right? For the next I steps, okay, so you have some number of steps here, where I denotes the prediction I steps ahead. Okay, so this is kind of where we were seeing here in their little diagrams. Sorry, that the transformer doesn't just seem to output the value in the action at one time step, it outputs the value in the action for some number of time steps. So that's probably what's going on here, is there's like a kind of a look ahead. Okay, so I is typically small, and in our case, I equals 4, so there's a 4-step look ahead. And again, it's at 30 frames per second, and they do every 4th frame. So 4 times 4 is 16, it's like a half of a second look ahead. For each observed step t, the model is unrolled for, sure that's defined as well, observed step t. The model is unrolled for I steps and updated towards respective targets. Okay, so this is your actual loss function here, right? This is your loss function. You guys come from a supervised learning or some other field of deep learning, that's what you could think of this as. So what is this? Here you have a sum over steps I0 to capital I. So again, I is the little look ahead. So this is going to be the reward at time step I minus the reward at time step t plus I, right? So this is basically telling you what is the expected, like how much reward am I going to get over these next I steps? Or the difference between my expected reward and then the actual environment reward. So I think the hat here refers to, I don't know what the difference between hat and no hat. Okay, RI is observed rewards. Okay, that's it. So without the hat, it means the observed, and with the hat, it's the actual reward, I suppose. So this is the difference between the actual reward and the observed reward. And squared there, of course. Squared error means that you penalize things that are further away harder. Here, okay, you have a comma and then a difference. So this is a different function here, different loss function, or maybe it's not a loss function. I don't know why they would use the letter L if they didn't want you to think of the loss function. Here you have the value. So this is what you are predicting the value of that state is, right? It's kind of think of it like the reward again. Minus g of t plus I. G refers to value targets which are obtained during retrace. So retrace is a different type of reinforcement learning. Concept, I want to say, I don't know. But think of it like the retrace refers to the idea of tracing your steps, right? Like going back and looking at what you've done, retracing. That's kind of where the high level intuition should come from. Q values are very similar to a value function, right? At the end of the day, your value function is giving you the Q value. Is there a better definition for that? Q value reinforcement learning. Model free, again, not model based, to learn the value of an action in a particular state. Okay, yeah, okay, that's, now I remember. So there's a difference between the value and the Q value. The value is the estimate of the reward at a given state. The Q value is the estimate of the reward at a given state and a given action. So values are only the result of the state. Q values are the result of the state and the action. So they're basically the same thing. They're just, there's different inputs, right? So Q values, you have access to the state and the action. Just normal values, you only have access to the state. Again. Okay, obtained from one-step predictions. Finally, here you have another L, another loss, this time over pi, which is the policy or the action distribution. And here we have our good old friend, the KL divergence. So KL divergence is basically, you could think of it like it compares two distributions. KL divergence, you give it two different distributions and it'll look at both of those distributions and it'll roughly tell you how similar they are, right? And it's not commutative, which means that if you give it A and then B and then you give it B and then A, it's going to give you a different answer. But it is very popular and it does have kind of statistical rigor. It's like well defined, it's good, it's great, it works for a bunch of different distributions, and reinforcement learning people love it, especially since the outputs to the neural nets that they use are almost always distributions rather than numbers. So it's very convenient if you can just say, okay, well, I have this distribution that is being outputted by my model. How do I compare it to this other distribution here, which I don't know what it is. What is it? The action targets pi CMPO are obtained by reweighting the current policy using clipped, normalized, exponentially transformed advantages. What? Clipped means you're clipping something, right? So probably they're referring to the fact here that a distribution is infinite, right? You can, when you sample from this blue normal distribution here, there is a non-zero chance that you get negative 7,505, right? Because this tail goes on to infinity. So in the reinforcement learning context, you need to clip these distributions. So usually they'll clip them at -1 and 1. That's what this clipping refers to here. Normalized, again, another type of, you guys probably know what normalized means, but it's basically the same kind of thing. It's like, okay, well, you have to make sure that the output, this distribution is nice and clean, and we can actually put it into an action. And then exponentially transformed advantages. So the advantage is, I want to say it's this TD error. It's basically like, what am I gaining by performing this action? It's a kind of like there's a specific definition for it. I don't exactly recall what it is, but it's like some difference between these actions, like it's something like that. It's a measure of like what you gain by doing this. Muesli furthermore incorporates an additional auxiliary policy gradient loss based on these advantages to help optimize immediate predictions of action probabilities. Muesli remains a target network which trails the sequence model and is used for acting and to compute the retrace targets. So in reinforcement learning, right, one of the things that makes this a little bit more complicated is that in supervised learning, you have a bunch of data that's collected beforehand, and then you simply train on that data, right? So the data exists before the model exists, right? But in reinforcement learning, that's not the case, right? The data doesn't exist before the model. The model creates the data, right? Because you're taking that little brain, that little model, that little neural net, putting it into the environment, and it's collecting data, right? It's doing episodes, it's rollouts, trials, it's creating that data. So you have to have a model in order to collect the data, and then once you collect that data, you retrain the model on that data, and then you need to basically recollect more data. And that seems kind of straightforward enough if you just have one computer that is collecting and then training and then collecting and then training and then collecting and then training. But that's generally not the case. Generally, you have, especially in a Deepmind paper, you have thousands of computers, right? And so you have different computers collecting data and different computers training, right? Pushing and updating the network. So you end up having kind of this more complicated system where you have kind of a target network, right? You have a network that is actually being used to collect experience, and then you have a different network which is being updated, and then you basically have to update the network that is used to collect the experience periodically with the one that you've been pushing experience into. So there's a little bit more complexity there with different versions of the little neural net, different versions of the model that get updated at different times and are used to collect data. So there's a little bit of complexity there, but I don't think it's important necessarily. Memory architecture. Memory is a crucial component for adaptation as it allows the agent to store and recall information learned and experienced in the past. Prior distribution is actually a mixture of the current estimate of the policy, the outdated policy used to produce the sample, and the uniform distribution, with the latter two are mixed in as regularizers. What is this in reweighing the current policy? Okay, so I guess this is maybe what this CMPO pi here is. So this distribution here, which you're using the KL divergence to compare it to the distribution that you have at this particular time. Maybe that distribution is a mixture of the current policy, right? The current network, the outdated network, and then a uniform distribution. So why would you have a uniform distribution here? Probably so that you sample some things, right? So like in this normal distribution, right? This blue one here, for example, it's pretty much impossible for you to ever get this 2. I know I said it was, it's not impossible, but it's very, very unlikely that you're ever going to get a value of 2 when you sample this blue distribution. So one thing you can do is you can add a uniform distribution to it, which means that you'll take that entire little blue line here and then kind of like move it up, which means that it'll increase the chance, it'll give a little bit more chance that you sample everything within the range. And the fact that they're adding this uniform distribution and a couple of these too is actually probably why they're doing this normalization here. Agent architecture. For each time step, we embed and combine the pixel observation, goal, hand, trial, and time information, production rules, previous action, previous reward into a single vector. Okay, so this is the observation. That's what the agent has access to. And again, to me, this is why I kind of am a little bit of a hater when it comes to this idea that this agent is general, right? Because the observation space for this agent is a very, very, very specific vector with very specific sizes that contains very specific information that is extremely brittle to this exact type of task, right? You know, they're talking about here, oh, we have such a huge variety in tasks, but like this observation vector here is incredibly task specific, right? It's extremely limited to this exact problem, right? If you took out the goal and the rule and the trial info, like this transformer becomes useless. So this model is only useful in the sense that it can only work in environments that have this exact observation space. So it's something to think about. These observations embeddings pass in sequence to the transformer XL, big transformer here, whose output embeddings feed an MLP value head, MLP policy head. So MLP here, just multi-layer perceptron. You have the policy head actually determines the action distribution or the action, and then the value head gives you the value. And the Wesley LSTM model step omitted in the diagram. While slow gradient-based updates are able to capture the latter, they are often not fast enough to capture the former. The majority of work on memory-based meta-RL has relied on RNNs as a mechanism for fast adaptation. In this work, we show that RNNs are not capable of adaptation in our challenging, partially observable, embodied 3D task space. We experiment with 2 memory architectures to address this problem. Okay, so they're basically going to be comparing an RNN with attention with a transformer XL. I'm going to go ahead and predict that the transformer XL is better. But like sometimes you need to formally show people that the transformer is better than the previous king, which I guess was RNNs. So it's important to the reinforcement learning community that the kind of pinnacle of reinforcement learning, which is the Deepmind team, shows you via an ablation study that transformers are the way to go. And then you'll see kind of from this moment on, everyone in all the future reinforcement learning papers will use a transformer as opposed to RNNs. But I don't know, maybe they were going to do that anyways. Both memory modules operate on a sequence of learn time step embeddings and produce a sequence of output embeddings that are fed into the Muesli architecture. We show that both attention-based memory modules, Transformer XL performs the best, otherwise is used as the default memory architecture. Okay, so you heard it here first. Propose a simple modification to our Transformer XL architecture to increase the effective memory length without additional computational cost. Since observations in visual RL tend to be highly temporally correlated, we propose subsampling the sequence as described for RNN. Yeah, so this is kind of what we were saying, where especially at 30 frames per second, each subsequent frame is going to be almost identical to the frame before it. So you want to spread out that subsampling and give your model a bigger context to pull from. I use the word context there with a little bit of cringe because it's like there's context means a lot of different things. For the first 4 billion steps of training, we use an initial distillation loss to guide ADA's learning with a policy of a pre-trained teacher, a process known as kickstarting. Teacher is pre-trained from scratch via RL. And a smaller model size, 23 million transformer for the teacher and 260. Oh, interesting. Okay. So they're doing distillation, but it's not a bigger model being used to distill a smaller model. This is a smaller model that is pre-trained from scratch. I guess it's just hard-coded to the specific task, and then it's being used to teach the larger model. That's kind of interesting. ADA acts according to its own policy, and the teacher provides target logits given the trajectories observed by ADA. Distillation allows us to amortize an otherwise costly initial training period and allows the agent to overcome harmful representations acquired in the initial phases of training. Integrate the distillation loss. We unroll the model from every transition observed by the student. Minimize the KL divergence between all the action probabilities predicted by the model and the action probabilities predicted by the teacher's policy at the corresponding time step. So this is the actual how the distillation actually works, right? You have the teacher policy, the teacher neural network, and then you have the model policy or the model neural network, right? The output of both of those is a action probability, a distribution, and you're using the KL divergence to compare those two, and you want them to basically be as similar as possible. That's what the KL divergence tells you. It's how similar two distributions are. And you're doing that over all steps from I equals 0 to I equals capital I. Pi tilde corresponds to the predicted action logits provided by the teacher given the same observed history. Furthermore, we found it useful to add an additional L squared regularization during distillation. What do they mean by L squared? Okay, there's some kind of additional regularization that's happening in addition to this loss. Experiments and results. We evaluate our agents in two distinct regimes, a set of 1,000 test tasks, sampled from the same, and a set of 30 single-agent and 28 multi-agent hand-authored probe tasks. Okay, so not only is there a single agent in this environment, but it seems like in some of the tasks, there's multi-agent, there's multiple little agents inside this environment. And I love it when they do this type of stuff, right? Because then you can start to have more complicated things such as interacting, adversarial behavior, competitive behavior, cooperative behavior. Probe tasks, particularly intuitive, deliberately cover a wide range of qualitatively different adaptation behaviors. Total achievable reward on each task varies, so whenever we present aggregated results, we normalize the total per trial reward for each task against the reward obtained by fine-tuning on the respective task set. We refer to this normalized reward as a score. Okay, so basically you want to make sure that the reward is normalized per task, right? Because some of the tasks, there might be more rewards if you have to pick up more objects and you get a reward for picking up an object. But you don't want, if you don't normalize the reward, what's going to happen is that the reinforcement learning agent is going to basically prefer to kind of overfit to tasks that have high rewards. And it's not going to care about the tasks where it only receives a little bit of reward. So by normalizing the rewards into what they're calling here a score, basically it means that all the tasks are going to be just as important to the agent. Zero-shot generalization is assessed by the score in the case of only being able to given one trial interaction. And then few-shot adaptation is assessed by the improvement in score as the agent is given progressively more trials. For each K, we report the score in the last trial. Okay, so what do we have here? We have number of trials. So this is how many times the agent can attempt the task in a row. So the red line is only tries it once, right? Only gets one shot. It's zero shot. And you can see here, of course, the fraction of tasks with a score. So, and then the score. So I guess lower score is worse, and it makes sense that if you only have one shot, it's going to perform worse. But if you have 13 attempts to perform the task, it's going to obviously perform a lot better. And the adaptation gap that they're referring to here is the difference between 1 versus 13 trials here. Adaptation, the agent achieves 80% score on 40% of tasks, but this improves 70% of tasks. Okay, so they're trying to like come up with these like formal definitions for what generalization and adaptation and the adaptation gap means. I mean, maybe I stand on my soapbox here and say that like, hey, by kind of needlessly creating these definitions here, you're just kind of making it more confusing, but I don't know. We aggregate scores across a task set using one or more percentiles. When presenting individual probe tasks, we report unnormalized total last trial rewards per task for agents and for human players. So maybe this baseline here is humans. I don't know, maybe. Space of training configurations is large, comprising model size, autocurriculum memory architecture. So this is kind of, if you're doing like hyperparameter sweeping, right? This is all the different things that can vary within their experiment here. And of course, it's a very large space of hyperparameters to tune. So they say they basically keep them consistent. We caution the reader against directly comparing results between different sections. Okay, so different experiments are going to use different sizes of the memory, different sizes of the network, potentially different sets of the tasks. So some tasks are going to be more difficult than others. So basically saying don't necessarily compare the different experiments to each other. Show the performance of ADA when trained in the single agent setting. ADA's zero-shot performance, which is the k equals 1, the red line, okay. This matches the performance of a baseline agent trained only in a regime where each episode consists of a single trial. Okay, so the dotted line is not a human, it's the baseline agent, which I think is what they described up here. In the distillation, they described a teacher, which is a smaller model that is trained from scratch. And I think that is what the baseline is. Okay. Human timescale. Oh, wait up. Let's continue with this. Despite being trained on a distribution over a number of trials, now turn your attention to ADA's few-shot performance. Given more trials, ADA improves its performance on over 80% of the task set, clearly adapting at test time. Improvements are particularly strong when comparing zero-shot performance, but ADA keeps improving. We compare the performance of ADA to that of a set of human players on 30 held-out hand-authored probe tasks. Okay, so now they compare it to humans and how quickly a human is able to improve their score versus how quickly ADA is able to improve the score. And I bet you that ADA is better at playing this game than humans. Here we go. So you can see here the number of trials and then the human. So obviously, if you just give the human one trial, it's probably unlikely that the human can figure out what to do. But then eventually, of course, we humans figure it out and we figure out the game. You have to combine this object with this object and then move it over here. So we'll kind of figure it out, but actually we're still quite shitty compared to the reinforcement learning agent, which first doesn't really know what's going on, but due to its the fact that it's been trained on a million of these or billions of these little mini games, it's very good at figuring out the little mini game. This is a little bit of the size here. 533 million. 25 billion. 100 billion steps. These numbers are huge. Experimentation, success, and refinement. We report average performance and representative behavior of ADA on the probe task. Wrong pair disappears. This is like the name of the specific task. When given more trials, the top-down view images show representative last trial trajectories when given different numbers of total trials. A corresponding video for the case k equals 3 shows behavior across all trials. Okay, so here you have the human being compared to the reinforcement learning agent. Again, the thick, so this is the, when you see these plots in reinforcement learning papers, and you see a solid line, and then you see this kind of like a fainter, thicker line, which is a different color. What this means is basically that there is some variance to the human, right? It's not just a single human. They did this with probably a dozen different humans. and they're showing you the top human and then the worst human. So what they're trying to show you with this thickness of the line here is that there is some spread of human capabilities, and they're saying the true theoretical human performance is somewhere between the top of this thick line and the bottom of this thick line. So that's what the thick, like faded out lines mean in reinforcement learning. It's basically when there's multiple different lines and they kind of want to show you what the variance with the spread of those lines is. Okay, so we see here how there's the agent versus the human. There's kind of a clear point at which the agent learns to do something, realizes after the first trial that, oh, okay, this is what you want me to do, and then it very quickly gets a high score, versus the human actually gets confused. Okay, multi-agent. So now they're going to go into multi-agent situations. Train a separate agent on a mixture of fully cooperative multi-agent and single-agent tasks. In fully cooperative multi-agent tasks, both players have the same goal. So you have some situations where the agents have to cooperate. Nash equilibria comes from game theory. It's this idea of, in game theory, you're basically using math and probability and to define like what the best possible move is in a particular game. People have applied this concept to kind of poker and Go and any game like that. You can basically come up with these Nash equilibrium or Nash equilibria, and like this idea of like there is an optimal action to take, right, given a certain task. But to get back on my soapbox, on my hater soapbox, I would say that this doesn't exist in the real world. Game theory breaks down once you account for the basically infinite dimensionality of the real world. All these kind of formal things, such as game theory. Game theory is a little bit broader, so specifically kind of some of the ideas behind game theory, I think that much like the Markov decision process, they put you in a constrained mathematical box, which works well for lower dimensional environments such as games and simulations, but I don't think they work well in the real world, because the real world is much noisier and has like infinite resolution and infinite dimensionality, right? There's like, you can't reduce the entire state of the world into a single state and reduce the entire action space of the world into like some discrete set of actions. This gives rise to a variety of interesting strategic novelties that are absent in the purely single agent setting, including emergent division of labor and physical coordination. Yeah, so this is kind of cool. Like, I love to see this, and this is, I think, the coolest part of these Deepmind papers, where they have these little embodied agents, especially multiple of them, is that they're not explicitly putting in any information or any kind of reward that causes the agents to work together. It's just that the agents eventually learn to work together, which is kind of cool, where you end up getting these division of labors and coordination that happen, which is really crazy to think about, because that means that one of those little agents is able to predict what the other little agent is doing, which means that one of those little agents has a mental model somewhere within the weights of its little neural net of what the other agent is going to do. Which is crazy to think about, because to me, that's kind of like saying, like, in a sense, like, to me, that's, if you can externalize an agent like that being an agent, that means you have to have some kind of internal model of what you are and what you're doing. And as soon as you do that, to me, that's kind of the definition of consciousness. So like, I feel like these little robots here, they're conscious. And I'll fight with anybody who doesn't think that. I think we're already creating consciousness and killing them billions and billions of times in these reinforcement learning papers or experiments. For the first time, we demonstrate can emerge at test time in few shot and held out tasks. Self-play outperforms co-play with a random action policy by a large margin. This indicates that the agents are dividing the labor required to solve the task, thereby solving the task more quickly. Cooperative self-play, random action co-play. Cooperative self-play, random action co-play. So cooperative self-play, this might mean that it's the same policy, the same agent is being used for both of the players in this two-player game. Use the purple core, we evaluate Ada twice per task and then playing with a random action policy co-partner. So random action policy co-player basically means they're playing, there's two little agents in this game, and one of them is basically just taking random actions, so it's kind of useless. All right, once we get to 2 hours, we're going to stop this because this is going to get a bit ridiculous, but I don't think we're going to be able to get through this whole paper, so maybe let's start looking just at the figures here. So here they have a pass over the wall game. Oh, it's actually pass over the wall repeatedly, so I guess it's just how many times you can pass an object over the wall. Okay, here's another interesting figure here. We have the impact of the architecture. So you see here transformer or RNN with attention, and then recurrent neural network. So guys, if you didn't already know it, the transformer is the best. Look at that. Look at that. Look at how clean it is. The RNN is actually worse. It actually gets worse over time. And then here you have curriculum. So you have PLR, no-op, and uniform. So different forms of the curriculum. And obviously PLR, which is the one that they talk about, is going to be the best one. Architecture influences performance. Of course, transformers are better. Auto-curriculum learning improves performance. Emergent curricula for a no-op filtering in PLR. Plot shows a selection of task metrics for the dynamic training set, averaged over all tasks with the standard error shaded. In all plots, a higher metric value corresponds to a greater task difficulty. For example, tasks with a higher number of rules require more trial and error to find the correct rules. Okay, so I think the number of rules, number of trials, number of dead-end rules, number of critical rules. So I guess this is just kind of showing you that over the course of training, the tasks that are chosen as part of the curriculum become more and more complicated. So you can see that at the very beginning, the tasks that are chosen have less rules than at the very end, which means that they're simpler, and then they become more complicated, and you see a similar kind of thing with number of dead-end rules and number of hidden rules. But interestingly, the number of trials, which is the number of times that the agent gets to try a specific task as part of an episode, does not change. It stays relatively constant. Scaling transformer parameters increases the median and test score. Yeah, so bigger model, better result. So you can see here that a 6 million parameter transformer versus a 265 million parameter transformer, you get a better score. This isn't as intense as I would have thought. I would have thought that would have seen a more exaggerated improvement here, but interesting to note. Because if you actually notice here, the y-axis here is actually kind of skewed. You see here, it's not exactly, it starts at 0.49, ends at 0.95, and the distance here between 0.86 and 0.95 is much bigger. So like it gives the appearance that there isn't as much progress as there is. Both axes are log scale. That's the terminology I was looking for. Scaling network size, memory length. So this is in attention-based architecture, such as a transformer. The memory is just how much of a sequence is available to the attention mechanism. And memory length is important because it actually determines the compute required. So kind of one of the main bad things about transformers is that they're very memory hungry, and the memory increases quadratically with the size of the sequence, the sequence length. Here, because the sequence is memory of a bunch of steps in an action or in some kind of environment, memory refers to the sequence, but that's just unfortunate terminology clash between the fact that memory and computing means different than memory in the context of reinforcement learning. But memory length here is basically the same thing as sequence length in a natural language processing context, for example. Okay, so they tried different sequence lengths or memory lengths here from 100 steps to about 700 steps. And yeah, you can also kind of do like a dilated convolution kind of energy here, where, hey, rather than kind of taking 100 steps that are right next to each other, let's kind of spread them out like that. And so we get a more, a larger context, right? Let's do it every 5 steps so that we have a larger effective memory length. Median adaptation scales. So adaptation scale is this score that they were, this thing that they defined earlier up there, where they said it's basically the difference between how many trials it takes you to get better. And I think roughly what they're going to show you is that the big transformer is going to do better. That's what you see here. Here you see the distillation. So distillation seems to actually perform better as well than from scratch. This is interesting. This is the teacher and the student. So the teacher trained from scratch, and then the student gets distilled from the teacher. You can see how kind of the on-ramp here is a lot more aggressive for the student because it has access to the teacher. ADA can leverage prompting with first-person demonstrations. I love this. I love that first-person demonstrations are now being called prompting. I love this kind of marriage of the ideas of in-context learning and prompting that are coming from natural language now being kind of shown in reinforcement learning and kind of changing the way that people do reinforcement learning. I think that's that's kind of like the best part of this paper to me, is like that the field of reinforcement learning is uh, willingly taking all these concepts and these ideas from other machine learning fields where they're having success and then applying them to reinforcement learning. Right, related work. So automatically curating, we combine the 2 pillars of AI generating algorithm. What? So here, comparing to a couple different things. Of course, procedural environment generation has been around for a long time. Schmidt-Huber did stuff there for sure. Open-ended learning. Again, I would kind of argue that this agent is not generalist. It's very narrow. It's very specific to this exact environment. Adaptation. This work focuses on a few-shot adaptation and control problems, commonly framed as meta-RL. Transformers. Okay, so actually, when was the first time that someone used transformers in RL? So obviously, with Deepmind and with such a large team, they had a guy who like did that. So this part here, this related work section, you can actually spend a lot of time doing this, right? So when you're writing a paper, like going through and finding all the different papers and finding the specific papers where people did similar things, especially in the world of reinforcement learning where the terminology is kind of a little bit more fluid and like uh, things like curiosity can change and somebody's was doing basically exactly what you're doing, but they were calling it something else. Like these sections can get very complicated, can get very difficult to populate. And unfortunately, what that leads to is that a lot of times people just promote their own work. So very often in a DeepMind paper, you'll just see a bunch of previous DeepMind papers referenced. And that's why people like, for example, Schmidt-Huber and Jan LeCun, like they're constantly complaining because they were doing a lot of these things decades ago, and then someone else does it now, and then someone like Jan LeCun and Schmidt-Huber say, hey, I was doing that, you should give me a citation, because as academics, they kind of live and die by the number of citations. So there's a little bit of unnecessary kind of antagonistic stuff going on in academia because like the citations are very important. But what was I talking about? Oh yeah. So either way, somebody at DeepMind, when they wrote this paper, spent a good amount of time, and I'm curious what it is, but I'm looking at all these dates here. 2021, 2022, 2017 is the original Transformer paper. 2020, this is NLP, NLP, NLP. Okay, so it seems like the first time anybody used a transformer in reinforcement learning was 2021. All right, let's read this conclusion and let's be done with it because I need to go eat breakfast. Yeah, we're almost at 2 hours, perfectly so. Adaptation to new information across a range of timescales is a crucial ability for generally intelligent agents. Foundation models in particular have demonstrated an ability to acquire a large knowledge base of information and apply this rapidly to new scenarios. Thus far, they have relied mainly on self-supervised and supervised learning. Would you consider contrastive learning self-supervised or unsupervised? I don't know. What about next token prediction? Is next token prediction unsupervised or self-supervised? I feel like most people would say next token prediction is self-supervised. An alternative to collecting datasets is to have an agent learn from its own experience via reinforcement learning, provided that sufficiently rich physical worlds or open-ended simulations are available. This is the problem. Rich physical world and open-ended simulations are not available. We demonstrate for the first time an agent trained with RL that is capable of rapid in-context adaptation across a vast open-ended task space. Yes, kind of, although I'll sit on my hater soapbox and say that this isn't as vast and as open-ended as they say it is. It's still very constrained in terms of the kind of appearance of the environment, the nature of the observation space, the nature of the action space, and so on. I would almost say Gato is more open-ended and more vast because of the fact that the architecture can account for different input modalities and different outputs. ADA is amenable to contextual first-person prompting. I think this is the most interesting part of the paper to me. This the kind of human expert demonstrations as prompts in reinforcement learning rather than human expert demonstrations as as something that you would use in supervised learning, kind of with the idea of behavior cloning. So I think this to me is the most interesting idea in this paper. Analogous to prompting in large language models. Our training method is based on black box meta RL, previously thought of as hard to scale. Yes, but I don't think they answered that because they trained it for a very long time on a lot of computers, so it seems like it is still hard to scale. We show that state-of-the-art automatic curriculum can shape the data distribution to provide sufficient signal for learning. Moreover, we demonstrate that attention-based architectures can take advantage of this signal much more effectively than purely recurrent networks. So make sure to use transformers in the future. If you're not using transformers, what are you doing? And distillation as a little trick to speed up training. Provided a recipe for training a 500 million model. Given scaling law trends, such models may be the future, become foundation models themselves. Cool, so very nice little cool paper. Very deep-mindy, you know, lots of very, very good figures. Lots of very, very cool videos. Yeah, nice little cute paper. I'm glad to see that reinforcement learning is staying up with the times. They're using transformers. They're starting to play with these ideas of context and prompting. And I'm excited to see what happens. I hope to see that they try to move out of these simulated environments and try to adapt them to a little bit more real world stuff. I know that they tried to do that with some robotics, but I hope that they push more into the real world, more robot stuff, more real world stuff. I think we read a paper where they were applying reinforcement learning to HVAC systems. I think that's good. I'd like to see more of that, right? But yeah, we're right at the 2-hour mark, so I'll end it there. Hopefully you learned something. Hopefully you're interested, and hopefully you'll go out and maybe read some more about this. Let me know what you guys think. Feel free to drop on the Discord and ask questions. Yeah, and like and subscribe, and talk to you guys tomorrow.